Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Morales. Thanks for meeting with me during office hours to discuss my project on early warning systems development.
Good afternoon, Jason. I read your outline. You want to focus on seconds-based alerts for earthquake response, is that right?
Yes, I want to understand how systems can give useful warnings in just a few seconds, and what trade-offs developers face.
Okay, let us start with the basics. Early warning systems detect the first fast P wave, estimate the event location and magnitude, and then issue alerts before the slower S wave and the strongest shaking arrive.
I know that P wave arrives first, but how do systems estimate magnitude so quickly without waiting for the whole rupture to finish?
There are rapid magnitude estimation algorithms that use initial P wave amplitude and frequency content, sometimes called saturation-aware estimators. We also use on-the-fly finite fault models for large events where standard magnitude measures underestimate shaking.
You mentioned finite fault models. Does that mean some systems switch methods as more data comes in?
Exactly. The initial seconds rely on empirical scaling from P-wave features for speed. As additional stations report, the system refines location, centroid moment tensor, and then applies a finite fault inversion to predict shaking patterns over a larger area.
What about sensors and network design? How much does sensor density affect warning time and accuracy?
Sensor density and low-latency telemetry are crucial. Dense seismometer arrays reduce blind spots and provide earlier confirmation. High-quality GNSS stations help for very large, slow ruptures, where seismic amplitude misses the true magnitude in the first seconds.
So systems like Japan and the West Coast network in the United States would differ because of sensor coverage.
Yes, Japan has a very dense national seismic network, so their system often provides longer lead times for many urban areas. The Shake Alert system in the United States covers large regions, but warning time varies based on distance to epicenter and station spacing.
Can you explain the trade-off between speed and accuracy when issuing a seconds-based alert?
Providers face a choice. If you wait for more data, you get more accuracy and fewer false alarms, but some people will have already felt strong shaking. If you issue alerts faster, you increase lead time, but you risk false or overestimated alerts. System designers pick thresholds to balance that risk.
What kind of thresholds are we talking about?
Thresholds can be detection confidence, minimum number of reporting stations, or predicted peak ground acceleration levels to trigger automated actions. For example, a school fire alarm integration might require a higher confidence than an app notification.
How do developers reduce false alarms while still keeping the warnings fast?
Several strategies help. One is combining seismic and GNSS data for independent confirmation. Another is machine learning classifiers trained on labeled event and noise data to recognize common false triggers. Edge computing at sensor nodes also pre-processes signals to remove local noise spikes.
Machine learning sounds promising but also risky. Do you have to retrain models often?
Yes, models need regular retraining as network configurations change and as new noise patterns appear. We also maintain conservative fallback rules, so that if the model's uncertain, the system falls back to traditional threshold checks.
What about communication systems? Once detection is made, how do we get alerts to users in seconds?
The backend must have prioritized routing. Messages go through redundant channels like cellular broadcast, internet push, and dedicated siren controls. Low-latency messaging infrastructure is essential, and dedicated APIs allow schools, utilities, and transit operators to receive and act on alerts automatically.
Could you give a concrete example of automated action?
A common example is automated train braking. If predicted shaking exceeds a threshold for a rail segment, the system sends a command to slow or stop trains. Another is shutting down gas valves or pausing surgical procedures in hospitals when strong shaking is predicted.
How do teams test and validate these seconds-based alerts before deploying them live?
There are staged drills, historical replay using past earthquake waveforms, and shadow mode operations where alerts are generated but not sent to the public. Shadow mode helps compare predicted outcomes to what actually happens and calibrate thresholds.
Do you work with emergency managers when you design alerts?
Absolutely. We involve emergency managers and community stakeholders from the start. They advise on acceptable false alarm rates, critical action thresholds, and message formats that are clear in high-stress situations.
You mentioned message formats. What makes a seconds-based alert message effective?
Clarity and brevity. The message should state the action to take, the expected intensity, and the areas affected. It should avoid technical jargon and provide immediate instructions like drop, cover, hold on.
What are the main research challenges remaining in early warning systems development?
Key challenges include extending lead time for near-field areas, improving magnitude estimates for complex ruptures, reducing latency across heterogeneous networks, and creating robust human-machine interfaces so people trust and act on seconds-based alerts.
Are there any promising new technologies on the horizon?
Yes. Distributed acoustic sensing on fiber optic cables offers ultra-dense coverage in urban corridors. Also, low-cost MEMS sensors enable community networks. Combining these with improved algorithms and better communications will strengthen seconds-based alerts.
For my project, I want to analyze trade-offs and propose a threshold strategy that suits transit systems. Do you have suggestions for next steps?
Start by reviewing case studies from Japan, Mexico, and the United States. Then simulate station layouts and latency scenarios. Include stakeholder interviews with transit engineers to determine acceptable actions for different lead times. I can help you design the simulation parameters.
That would be great. One last question. When you choose thresholds, do you ever favor detection over false alarms?
Yes, we sometimes choose thresholds that favor detection over false alarms, because missing a major event can cost lives. That means we accept a certain rate of false alerts while we refine the system and educate users.
Thanks, that clarifies a lot. I will draft my simulation plan and bring it to you next week.
Good, I look forward to reviewing it. Remember to include both technical metrics like latency and practical outcomes like expected casualties avoided for different thresholds.
Listen again to part of the conversation, then answer the question.
Yes, we sometimes choose thresholds that favor detection over false alarms, because missing a major event can cost lives.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit spinta.org.